All right, I am live. I'm back working on some more specs again. This is the follow-up from last week. So last week we just kind of were refactoring some interop specs. Not gonna lie, specs, they're a mess. We've got a long way to go making them cleaner. So this is my way to just block off time and make sure that, we can prioritize um, writing the specs. Let me just show myself really quickly on Twitter. Come, rewrite the OP stack interop specs with me. Get your, comments on specs.optimism.io. Why does X do that thing where they, block links? All right. Cool. So now we got focus time. Focus time is great. Nobody, no Slack messages, no Discord messages. So let's take a look where we're at right now. So yesterday we went through and we did some of these interop specs. So we rewrote this a little bit. These are our definitions. We have a source chain, destination chain, initiating message. So one thing, I think maybe we want to change this initiating message. It's too abstract. I think we want to change it to initiating log, but not gonna do that there. Do that now. I think now let's look at the pre-deploy. So this is a long one. Very long. Let's see. This one could probably use some love. Let's start at the top. So we got this 4 new system level pre-deploys are introduced. All right, I don't like this. It's way too easy to go out of date when we use numbers. So I want to avoid numbers. Look at this. We got some autocomplete. I'm testing out cursor. I used to be a NeoVim maxi. I still kind of am, but I got a new laptop and I didn't port over my VimRC. Actually, what happened was the VimRC broke when I tried reinstalling it on my new machine. Just never made a new one, alas. So, okay, let's see. So we want to say something like, interop introduces new pre-deploys that facilitate cross-chain messaging and token bridging. Wow, I love when AI thinks faster than I do. Okay, so let's just delete this. All right, so we got our cross L2 inbox. This is our address. I think maybe we should consider making a table that is like, like, I don't want that. We want something like, constants. Let's make a little constants table. Like, name. You can do like value. And let's do like type. We only need 3 sections. Okay. That is exactly what I wanted. Thank you. Now we just want to like do that. Perfect. Do that. Do that. Oh, all the boring stuff is done. Um, hmm. Now, are these correct is the question. Cross L2 inbox is 22. That is correct. Let's just do like pre-deployed addresses. I don't love this camel case. You cross L2 inbox. All right, are you going to be smart enough? Yes. Wow. Thank you for being smart. I love the future. The future is great because we can spend more time doing the interesting things rather than memorizing, Vim macros. Even though Vim macros are pretty fun, I want to be doing things that are more fun. All right, so we got our cross to L2 inbox. We got the L2 to L2 cross to main messenger. We got the L1 block, optimism mintable ERC20 factory, and the superchain token bridge. Okay, so like these, redeploys are added or modified as part of the, call it interop network upgrade. Now this makes it a little bit easier to navigate. Is it like possible to do like a link? Maybe it's link, do that. Let's see, I do. It's smart. Boom, boom, boom. All right. So we're making progress. So, developer lands on this page, we see the addresses at the very top, very concise, easy to see. You can get information and links directly to what you care about right at the very top. So cross L2 inbox is 22. Delete that. Okay. So let's start with, is the system pre-deployed for cross-chain messaging? Anyone can trigger the validation of cross-chain messages on behalf of any user. Okay, so maybe what I want to say is the, it is the, central pre-deploy for cross-chain messaging. Any cross-chain message must be, must pass through the cross L2 inbox on the, I want to say, must pass through the destination scenes cross L2 inbox for it to be considered, authenticated. I feel like there's a better word than that, but like any anyone can validate any initiating message on behalf of any user. So these messaging invariants. Come back to those. Looks like this was wrong. This is not right. This is why you always gotta double check AI. We can just do like, cross L2 inbox is, yeah, like that. Get rid of the .md. Wow, go-to definition for Markdown is very nice. Okay, L2 to L2 cross domain messenger. Nice. Okay, you learned. The AI learned. Okay. So nobody is let me see if people are leaving comments. Sorry. No comments. Oh, it says click to join the chat. Hmm. Will it take me out of the stream? I don't know. All right. I'm not going to click it. I'm sorry. I'm just going to write some more specs. All right. So cross L2 inbox, central pre-deploy for cross-chain messaging. Any cross-chain message must pass through the destination chain's cross L2 inbox for it to be considered, safe to consume. They're like, it is permissionless. To validate any initiating message on behalf of any user. There is no replay protection, and initiating messages should be thought of as similar to it's like, any cast UDP packets. Let's get us a Twitter, or not a Twitter, a Wikipedia. Anycast UDP. Is Anycast the best? I don't think Anycast is the best. Like UDP. Let's just get rid of that. There is no replay protection, but it can be built at a higher layer. So we have these messaging invariants. Okay. Now validate message. Emits the executing message event to signal the transaction as a cross-chain message. What happens if I follow this? Wow, go-to definition is great. Okay, so we got our identifier. Where's executing message defined? Perfect. Perfect, perfect. Do that. I can go to. All right, perfect. Okay, so validate message emits the executing message event to signal transaction as a cross-chain message that must be validated. This function should be called by applications that so the following fields are required for validating a cross-chain message. So we have this identifier and this message hash. Check 256 hash of the message payload matching the initiating message. Of the message payload representing the initiating message. Right, so basically, right, you have this identifier, and the identifier is a pointer. Right, so we go here. The identifier uniquely represents a log that is emitted from a chain and be considered a unique pointer to a particular log. No class in the derivation pipeline. It's really like I guess I'll leave that for now. But yeah, basically the full node software collects up all these identifiers that are emitted from one chain and then goes and checks on other chains that the identifier and initiating message pair match. Omitting the hash of the message is more efficient than omitting the message in its entirety. Quality with the initiating message can be handled off-chain through hash comparison. Let's get rid of this reference implementation. But do we have a section in here, deposit handling? Okay, we got a section on deposit handling. Okay. You know, like, let me just say example integration. I don't think that this really makes sense for the specs, but it's in there. Let's not change it too much right now. Okay, so deposit handling. Any calls to the cross L2 inbox that would emit an execution event will revert. Must revert if the call is made in a deposit context. Let's add a link. We figured out how to solve this. So basically right now the problem is that deposits are force include, right? So if you force include a transaction that if you force include a transaction that basically breaks the invariant, then the invariant that all executing messages must be valid, then you can just cause consensus instability and have the chain infinitely reorg. That would be bad. So this issue. For more information. Okay, so we'll just enshrine the issue right now. That's the basically, what we're thinking in doing at a high level. Basically, we want to, allow for deposits to trigger executing messages through this two-step process. And we have it spec'd. Wonderland made a prototype implementation. It's great. It's just a prioritization issue at this point. We know how to implement it. Okay, so identifier getters. We no longer need this because previously, like when we first designed interop, we were thinking that we wanted to do this thing where you basically only allow EOAs to send the cross-chain transactions that on the executing side. And this basically allowed for static analysis of like pulling out of like the call data. You can pull the executing message out of the call data rather than pulling it from the event. And doing that was really nice because then we could, have like strong DOS protection. But then 3074 was, being considered at that time. And then it became 7702. And basically these EIPs prevent you from reliably knowing within the EVM if the transaction is in the top level of the call frame, um, or like the call is coming from like the top level. Um, you basically need to enforce that the call is coming from the top level, and you could only do this with like the is EOA check, which is like TX origin equals message sender, um, because that would you basically be able to like um, in the case those two are equal, the call is coming from the top level from an EOA directly. But with 7702, this is no longer possible. You can get around that because it could be like a sub call through like a call back to the smart contract wallet or something. So yeah, we ultimately removed this idea of like only needing the EOA or only allowing the EOA to send the cross-chain message. And in doing so, we open up ourselves for DOS because now it requires execution to execute the transaction to know if it's valid. You have to execute it and then you have to grab the logs that it produces. And basically, our reasoning here is that block builders are supposed to be smart and, you know, we can engineer the DOS protection at the block builder level. So that was our thinking there. But everyone in the ecosystem seems to be happy that we removed this like only EOA constraint because it makes smart contract wallets like in relayers like kind of useless for sending cross-chain transactions. Cool. So now we're taking a look at the L2 to L2 cross-chain messenger. So this is the next contract. So let's get rid of this address of this message version. Okay, so the L2 to L2 cross-chain messenger is a higher level abstraction on top of the cross L2 inbox that provides general message passing. Um, the main use case um, the main use case um, no, utilized for secure transfers of ether or token between L2 chains. Cool. Messages sent through the L2 to L2 cross-chain messenger on the source chain receive both replay protection as well as domain binding. AI completion for writing docs is crazy. I lose my focus immediately. Uh, the AI, maybe the AI can focus for us. Let's see. Okay. So we got replay protection and domain binding. So L2 to L2 cross-chain messenger gives replay protection and domain binding. It provides like a much more simple interface for users. So let's think what we're missing is like a kind of thing. They're calling this functions. Let's call this interface. To interface. So let's grab, there's interfaces. So the L2 to L2 cross-chain messenger uses a similar interface to the L2 cross-chain messenger. This is true. That's like the L1 to L2 bridge. But we learned a big lesson. No gas introspection. Gas introspection is bad. Very, very bad. If you're passing a gas limit. Okay, so you do need it for L1 to L2, but you don't need it for L2 to L1. Basically, you need it for when there's force inclusion. If you don't have force inclusion and you're doing gas introspection, then you're going to have a bad time. Okay, so here's send message and relay message. And this is for 105 makes sense. I don't think just 5 is 5 supported. Or okay, let's see. Let's take the send message invariance here. Okay. No. You must be 4. And you must be 5. Okay. So this is how you get the replay protection, these invariants right here. Okay, so send message, destination, address, message, turns the bytes 32. And this is like, the message hash. What is the message hash? Ivan. Cool. All right, so following function is used for sending messages between domains. Here's this. Here we go. Okay, here we go. It returns the hash of the messages being sent. The destination is enforced to not be the local chain. Did we remove that? I'm pretty sure that we removed that. Let's double check that. L2 to L2 cross domain messenger. Yeah, we still have that invariant in there. Okay, let's leave that. There's no need for address aliasing. Okay, perfect. Let's make a section for this. address aliasing. Yeah, we got rid of address aliasing. Like, let's say the send message not intended to be used for sending ether between chains. Okay, perfect. Send message invariance. Now we're under relay message. So we can delete this. Let's grab this. Okay, here we go. This is good. Believe that this matches down there. With the identifier, send message, external payable. Okay. Let's move this up here. Move this up here. So here's our relay message function. Okay, so geez, my laptop is a little crazy sometimes. All right, so let's figure out where we are. So relay message. So relay message is like this second half of the cross-chain message. First you do send message, then you do relay message. And I've just spent like maybe the last 10 minutes just trying to clear these up a little bit. So first, you do the send a message. This is the function interface for send message. So now let's get a clear function interface for relay message, right? So the way that these hook up together is basically, user calls send message under the hood. They pass the destination. So this is the chain ID. So maybe I want to like include the used to send, it is used to initiate a cross-chain call on a remote chain. Okay, so the send message function is used to initiate a cross-chain call on a remote chain. So basically, like the arguments, we got the destination, the target, and the message. The destination is the chain ID. The target is the chain, like the address on the remote chain, and the message is like the call data. So it is, permissionless to call. And is permissionless to call. Um, is yeah. So now, like, I want to say something like, you know, the destination. Okay, perfect. Destination is the chain ID of the remote chain to call. The target is the address of the contract to call on the remote chain. The message is the call data to call the contract with. Okay, I'm not sure if this should go on a table, but I'll just do this for now. Let's put this below it. So we know the inputs, we know the outputs. It returns the hash of the message being sent, which is used to track whether the message has successfully been relayed. It must emit a sent message event with the necessary metadata to authorize the execution of the message when relayed on the destination chain. Yeah, so events are how you authorize cross-chain messaging systems built on the OP stack. Okay, so we got send message. Okay, an explicit destination chain and nonce are used to ensure the message can only be played on a single remote chain one time. The destination is enforced to not be the local chain to avoid edge cases. Send message function is not payable as it is not intended to be used for sending ether between chains. Okay, perfect. Let's see. So we got this address aliasing section. There's no address aliasing. Maybe I want to say something like, you would need address aliasing if the address aliasing would need to be implemented if the top level message dot sender value was set. Basically, like on the initiating side, he sent a cross-chain message. Then if that top level message sender on the executing chain was set to the value from the initiating chain, then you would need address aliasing. So how do I word that in a way that like is easy to say? I don't even know if people understand me. Basically, it's like you only really need it if the EVM context is modified. So you send the initiating side of the transaction, and on the executing side, the top level message sender is like the relaying account. It's not the sender from the initiating side. So address aliasing would need to be implemented if the top level message sender value is set based on the caller of send message function. This is not the case, and this is not the case. Would require a diff to the EVM spec. Okay, so Hmm. Okay. There is a way to implement this with 7702 though. Um, won't go into that rabbit hole now though. Okay, so we got some invariants. Um, can I get local chain? I don't really know if this is like a strong invariant. We could probably delete that. Um, a locally defined nonce must increment on every call to send message. Perfect. Much cleaner. Let's see, what time is it? Okay. All right. Drew says, what is a nonce? It's incremented for messages with the same hash, with counters stored per hash. Yeah, so a nonce just is like something that ensures that the um, message can only be used once. Um, you basically mix the nonce into the message hash. Well, actually, no. Like, okay, specifically, what the nonce lets you do is it lets you make the same call twice, right? Because we have to hash the data for replay protection and put that into storage. So you can imagine if we didn't have a nonce and you tried to make the exact same call to the contract with the same call data, right? And we didn't hash in a nonce, then the hash should end up being the same, right? So we use the nonce to basically increment um, and change what the hash is by including it into the preimage, right? So if you look at the send message function as a destination, a target, and a message, right? So if we want to have replay protection, what we need to do is we need to hash that information together, put it into storage, and assert that the same data isn't being sent through twice. But maybe you want to make the exact same call twice to the same destination chain, same target chain with the same message. If we hash that, then it would, if you hash the same preimage twice, you get the same digest twice. So how you enable the same cross-chain call to be made multiple times is you mix a nonce into the preimage, the information that's being hashed, and then you basically hash it, and then you um, can like make the same cross-chain call because you'll get a different nonce the next time. And because hash functions are nice and we have pre-image resistance, basically meaning like, different input will result in different output to the hash function. Um, you can basically make the same cross-chain call multiple times. So that's why there's a nonce. All right, so we refactored the send message, we refactored the relay message. We're not done yet. Uh, okay, so let's relay message. Um, so what does the relay message function do? Um, the relay message is used is used to relay a message is like it makes up the second half of a cross-chain message. The um, the the call, uh, the call sent you know, I want to say like the call in the call made to send message is, it ends up being called through relay message. Like relay message triggers the call that was made to send a message. Um, um, executes when relay message is called on the destination chain. Cool. All right. Yo, what's up, C node? Yo, help me with the specs, and your words will go on the specs website. Everyone will see them. Right now we're talking about relaying messages. So we got this relay message function. Basically, the relay message function makes up the second half of a cross-chain message. The call made to send message executes when relay message is called on the destination. So the call made to send message, it's like a pair. Like how do I word this nicely? A user calls send a message on chain A, and then they call relay message on chain B, and relay message executes whatever was passed to send message. Cool. All right. So I'll continue here. All right. So when relaying a message through the L2 to L2 cross-chain messenger, it's important to require the destination be equal to the blocked out chain ID, blah, blah, blah. Why is my computer broken? Okay. Let's talk about the inputs. Inputs, and then we got variance. So basically, the does the AI want me to type? ID is the identifier of the sent message event that was emitted by the send message call. The sent message is the serialized sent message event. All right. Yeah, I think that's good. That follow how. Okay, great. The perfect. So we got send a message. Send a message is looking good. We got relay message. Relay message is still a little bit not good. Okay. When relaying a message to the L2 to L2 cross-chain messenger, it is important to require that the destination chain be equal to the blockout chain ID. Okay. So we have that in our invariants. Okay, so this section is useless. It is important to ensure that the source chain is in the dependency set of the destination chain. Otherwise, it is possible. Okay. So, like, dependency set management. We can say the L2 to L2 cross domain messenger. I don't want all this. Has no legibility of the dependency set. It is up to the off-chain software to um, ensure that only, you know, that, you know, messages from the only messages from the dependency set can be relayed. Um, Messages from outside the dependency set will be reorged out of the chain. Cool. That's probably a confusing point. It's important to ensure that the source chain, okay, we can delete that now. Um, a message is relayed providing the identifier. Wow. Wow. We're good. That's, yeah, it's fun. All right. Note the relay message function is payable to enable relayers. The relay message function is payable to enable relayers to um, earn for relaying messages. Okay, to enable cross-chain authorization patterns, both the sender and source must be exposed via public getters. Um, okay, this does not make sense. Why is my laptop freaking out? Okay, so we need something like, wow, we just don't have anything on this. So this needs to be made into its own section. Okay. Um, okay, off-chain software meaning L2 block builder and L1 bridge contract. Yeah, great question. So the off-chain software, that is like the full node. It's like, Geth, like the execution client, at least for the OP stack. We kind of have like a similar distinction between an execution client and a consensus client, just like L1. L1 has like kind of, two parallel tracks, execution and consensus. So OP stack has the same thing. In the OP stack, the consensus layer basically does this process, what we call derivation. It is like a big map reduce over L1 data to turn it into the inputs to the execution layer. So the off-chain software can validate all the cross-chain messages and reorg out blocks that include invalid executing messages. So, like the same way that the consensus layer finalizes L1 blocks, we have our consensus layer, it finalizes L2 blocks. And the specs go into a bunch of detail about the rules about how these L2 blocks are finalized. Do unfortunately need to go because mhm, I need to do an interview, so I need to go. But this was fun. I think we learned a little bit. Definitely, the specs need some love. They need some cleaning up. They need more work. Today we got to go through the pre-deploys, the L2 to L2 processing messenger, and the cross L2 inbox. These are two important smart contracts. The pre-deploys. Pre-deploy is kind of like a precompiled, but it's EVM bytecode instead of like a native, implementation of some functionality. And we use pre-deploys specifically to not break tooling like Foundry, right? Like it's really annoying if you like can't just use Foundry or Hard Hat to like write your tests. So we always use pre-deploys when possible, because it won't break tooling. So yeah, we have the L1, the cross L2 inbox. This is like the kind of main central contract for interop. And we have the L2 to L2 cross-domain messenger built on top, which basically these two contracts together allow for simple cross-chain messaging. Yeah, so I'll be back again. I hope to go deeper into this with y'all and rewrite all these docs. Thank you, Ellie. Very kind words. Appreciate you listening in. Shout out to all the listeners. And just throwing this out there, would love to get your voice in these docs. If you want to live on specs.optimism.io, give me some suggestions in the chat, and we'll get you in the specs, because we're going to build these specs together. They're going to be really nice. Everyone's questions are going to get answered, and we're going to ship interoperable Ethereum. Cool. How do I stop this now? No. Okay. Recording. No.